Hey everyone, I am Dr. Abdul Aziz Abdul Aliyu, a senior lecturer in the Department of Materials, Manufacturing and Industrial Engineering, Faculty of Mechanical Engineering, University Technology, Malaysia. I am with you today to present a very important topic in the area of manufacturing, that is design for additive manufacturing. So at the end of this lecture, you are expected to understand the principles and importance of DfMA and identify constraints and opportunities unique to additive manufacturing. Apply design strategies tailored to additive manufacturing processes, and finally explore some real-world case studies showcasing design for additive manufacturing. Before we go further, we need to understand the definition of additive manufacturing. Additive manufacturing technology has been with us for decades in existing. Now, only that we didn't realize it until recently, around 1980s, when the concept was introduced in MIT University. You can see this is an insect using the concept of additive manufacturing and creating its own nest with saliva as a raw material and the branch of a tree as the substrate material. So this is the concept of additive manufacturing, which had been in existence for so many years. So additive manufacturing is nothing but layer by layer fabrication of 3D components realized from computer-aided design. It is an automatic process which is used to produce various objects in form of prototypes, tools, and even assemblies. And it do not require any cutters, tools, or any pictures. Additive manufacturing process can be done in mainly 3 stages. The first stage is pre-process, which involve the realization or the formation of a CAD file. And then this CAD file need to be converted into the language that the machine can understand, referred to as STL file. That is converting the CAD model into stylistic format. And this format consisting of various number of triangles. So this is a kind of file that understand by the machine. And after this, then you need to slice it to allow you to use the concept of additive manufacturing, that is deposition layer by layer to form the final parts. Then you need to have a support. The support is important in such a way that it will help you in holding the components that you intended to produce. If you are depositing in the middle part of the substrate, this wouldn't have an issue. But the main issue is if you are producing or depositing the parts at the edges of the substrate, this will result in overhanging. In such a situation, you need various supports at the end of the object to avoid its failure, maybe by falling down or producing components beside the shape you intended to produce. This is similar in the case of building of certain components. You can see that this is a kind of overhanging which require to put the concrete, and after the concrete is being cured or dried, then all these supports in the form of scaffolds need to be removed at the end. So the same goes to additive manufacturing concepts. So you need to build the part in additive manner or stacking manner. And then the last stage is to use post-process by breaking or removing the support, and then finishing process to have the desired surface finish for such a component. Now let's have a glimpse on various kinds of additive manufacturing, specifically metallic additive manufacturing processes. These are mainly classified into direct and indirect processes. In the indirect processes involve indirect deposition on a metal, deposition of either wax or plastics on a metallic mold, which enable use in metal casting. So it will help in creating certain impression or patterns that is required to appear on the final parts. While the direct additive manufacturing processes produces the components directly after deposition. So we have four main kind of them. We have beta jetting, which mainly used in bonding liquid agents to form a component. It's normally in the form of powder materials, and it may be metal, plastics, or ceramics. And another form of additive manufacturing is powder bed fusion, sometimes called selective laser melting. It normally used powder, as the name implies, and selectively deposited on the specific area or design area to form the object. It normally uses a laser or electron beam melting, and this process is applied to metals only. The next method is sheet lamination. This sheet lamination process, as the name implies, it bonded sheets of metals, sheets of material to form components. The material might be a metal, paper, or wood. And the last direct method is direct energy deposition. So in this situation, it's just a deposition of metals or materials in the form of wear or powder using laser or electron beam melting. The beauty of this method compared to other metal processes is that it is used in repairing the worn out components or broken down components. So now let's go into the main topic, that is design for additive manufacturing. So design for additive manufacturing is nothing but to think or to design parts to leverage various capabilities of additive manufacturing. Before this, I want you to understand that additive manufacturing is not here to replace the existing conventional processes. Rather, it is designed to help in realizing components that are difficult to produce using conventional methods, that are so complex, which cannot be realized using conventional methods. So that's the main purpose of additive manufacturing. And this cannot be done without design, definitely. So design for additive manufacturing is derived from design for manufacturing. So you need to design the parts in such a way that you have a better components. You have a good components that cannot be realized using conventional methods. So you have to go beyond design for manufacturing. You have to think out of the box. Think in various ways that you can have a better design. So just look at these components. Look at how complex it is. Simply, you may say that this component is technologically impossible to reproduce using conventional methods, but it is easy to produce with additive manufacturing. Look at another component, which was produced using design for manufacturing by conventional methods. And this can be reproduced using additive manufacturing after design for additive manufacturing. You can see two different components. And all of these are expected to perform the same function. So that's the main purpose for design for additive manufacturing. You think out of the box. Design a component that will maintain the integrity, the function, the mechanical properties of the same component produced using conventional methods, while saving the material and reducing the weight, and also saving the cost of such final product. So there are four main key principles that is normally used in design for additive manufacturing. The first principle is to design for correct additive manufacturing process. You can see in the previous slides, I highlighted some classification of additive manufacturing process. And each of these additive manufacturing process has its own capability, has its own characteristics. So you need to select the best process that will give you a certain product at different production scales and at different cost, and also different geometric complexities. So you need to understand the strengths and weaknesses of various AM manufacturing processes so that you can realize the geometry of the parts that you wanted to create or produce. These are some guidelines. So you need to understand this guideline, which will help you to select the best additive manufacturing process to use in any certain part that you wanted to produce. So the second method is principle is design for minimum material. Saving material is directly proportional to the cost of the final product. Aside that, you can also produce a component that is light in weight. And this is very important in various manufacturing industries, especially aerospace and automobile. So there are three main methods that you can produce material with lightweight. The first one is topology optimization. You may also employ the system or the concept of lattice structure, or you may use a minimum support. So I will try to explain briefly each of these methods. That is like topology optimization is nothing but removing the unnecessary material while maintaining the mechanical property and performance of the component. So the tools you need in this situation is just solid CAD design softwares like ANSYS and Topology or SolidWorks. Just look at this is hydraulic manifold. This is initially produced using a conventional method. It contains about 13 components, individual parts, and it weighed around 16.2 kilograms. So all these components is redesigned and produced using additive manufacturing and consolidated into one parts. So you can see that you consolidated 13 parts into one, and the weight was reduced to about 90%, from 16.2 gram to 1 kilogram to 1.42 kilogram. The same goes to this component. This is weighed around 4.22 gram. And if this component was produced by machining process, and for machining, you need this bulk of material, which weighed around 10.39 grams. And utilizing the concept of topology optimization, you can produce the same components which weighed less than 1 gram. Just look at how you save the material and you produce a lighter weight components. The same goes to these components. You can see it was produced, consolidated in just one part. And initially it is 5 kg using conventional methods, and final part was produced with 1.3 kg. So the next is the employing the concept of lattice structures. We have various lattice structures or honeycomb structures. So you can employ this integrated on a certain components that require maybe porosity in its structure. just like these components or carburetor, you can see it requires some holes or porosities that will help in heat exhaust or fluid exhaust. So you can use this in a design to have one component or a consolidated component using this lattice structure. The same goes to human implant or human bone. We know that human bone is porous in nature, and the difficulty here is that the porosity is not uniform in size. And the density of the porosity also varies from the inner part to the outer part along the thickness of the bone. So you can only design this using by employing the concept of this lattice structure, and you can design it to have either solid to porous length. So another method is to optimize the design with minimum support. Because at the end of the design or the product, you need to remove the support which might become a waste. So you have to think any design that you can use to have a lowest or minimum amount of support. Building orientation is one of the key strategies. For instance, if I want to produce this conventional spring at vertical orientation, you can see that this is the amount of support which I need, which is highlighted in green color. And if I orient this to an angle of 45 degrees, this is the amount of support that I will need. And if it is aligned horizontally, this is the amount of support you can need. So you can see that from the design, you can understand which among the orientation will give me the lowest amount of support material. The same goes to these components. If it is horizontally produced, then you need this amount of support. If it is vertically produced, you need this amount of supports. However, research is ongoing how to eliminate the support, to produce a component without the support. And for this reason, a self-supporting geometry arises. So you may produce a component with self-supporting like this. So you can use some material that is less in cost and utilizing topology optimizing by producing some porosities along the self-supporting so that you can have the components with less support. So you see, if you use self-supporting in this component, you only need the base as a substrate or the supporting material. Look at how we reduce the support material significantly. If there is, that is why in design for additive manufacturing, we said that you have to think out of the box. Think any way that you can reduce the supporting material. Even if it will take you to use no support material, we will appreciate that. The next is design for improved functionality. There are numerous components that have various parts together, and which incorporating them will improve their functionality. Just like this heat exchanger, it contains various pipes which help in heating and cooling of fluid channels. So you can see by employing the concept of additive manufacturing, you can consolidately produce these, the fives and the frame part together at once. The same goes to this drone engine, which has a solid or dense part, inner part, and the porous outer part. So you can use the concept of lattice structure and design this part and produce a consolidated part with integral function. Then the last strategy is design for part consolidation. No matter the number of components contained in a part, you can consolidate it in one production by employing the design for manufacturing, additive manufacturing. Look at these components. Initially, this component has about 5 parts. So if you want to produce conventionally, you have to produce these parts separately and then assemble them together, which is quite tedious and time-consuming and costly. But with direct additive manufacturing method, you can produce it at once. The same with components that are mobile in nature. So you can produce them at once using additive manufacturing, which is quite tedious using conventional methods. So now let's look at some case studies that are available in the market. You can see this is a flow ducts. These contain a hole inside. So using conventional method, you can only produce the hole that are perpendicular to each other. And this, of course, results in fluid friction and reduces the smooth flow of the fluids. But with additive manufacturing, you can remodel such porosity or hole to have a curved surface, which will allow a smooth flow of the fluids. You can also design the thickness of the pipe by employing the topology optimization to have some porosity within the thickness of the pipe by reducing the weight and the material of such a component. You can also design for a minimum amount of support using design for additive manufacturing. Another case study is considering this hydraulic manifold. Also, it has a hole inside, help in exhausting the fluids. So you can see that the hole is also aligned perpendicularly. This is why, because it can only be produced, it is easier to be produced using conventional methods. But with additive manufacturing, you can make the hole to be in a cup, so it will have a smooth exhaust of the fluids. And also the frame can be designed to have some porosities, which will help in reducing the amount of material to be used, and also reduce the time to be produced, and of course the cost of the components. And this allows the smooth flow of the fluid. So before we call it a day, we need to look at the future trends of additive manufacturing. So in future, we are expecting additive manufacturing to be applied in various materials because currently only pure material can be used. And we are expecting additive manufacturing to be explored in 4D manufacturing, and also expecting the knowledge of artificial intelligence to be incorporated in design optimization for additive manufacturing, and also integration with bioprinting and tissue engineering. We are expecting additive manufacturing to be used in tissue printing, like natural tissues, like the organs, sensory organs, and other tissues in the human body, and also help in sustainability and circular manufacturing, like in the food industries and other companies that help in enhancing the sustainability. So in summary, we can say that DfMA enables performance-driven, efficient, and novel designs. Also, it embraces complexity and also reduces constraints. It is being applied, it has various applications, specifically in optimizing the components by using the knowledge of design for additive manufacturing. And it also helps in parts consolidation, direct part replacement, and also rapid prototyping and tooling, especially when low volume parts are involved. So aside numerous advantages of this process, it also have a number of limitations, like the dimensional accuracies and surface roughness. Actually, the surface finish produced using additive manufacturing is quite bad. And these depend solely on the type of powder size, the layer thickness, and layer energy used. And also the quality and consistency and wafting resulted from additively manufactured parts, which results in residual stresses. So researches are ongoing, like employing a based heat treatment or annealing process that can overcome this generation of residual stresses. And also the part size. The current available machines, additive manufacturing machines, has a size limitation. So we need to improve on this. And also the cost. The additive manufacturing machines actually are costly, and the same goes to the material also. And also in the material aspects, not all materials can be used in additive manufacturing. So we are exploring also, and research are ongoing to save this. So with this, I will say thank you very much for following me, and I hope you enjoy my lecture. Thank you very much for listening.